Okay, and welcome back to Engineering 255 Statics. This is the last video of the chapter 5. We're going to finish the chapter 5 by looking at the three-dimensional case for a rigid body. Now previously you were looking at the two-dimensional, that you have equilibrium condition, which is summation fx, summation fy, summation moment at a point equal to 0. We're going to extend this one to the three-dimensional and give you some idea about constraints and statistical determinacy. So three-dimensional, when you have a three-dimensional, how do you solve the problem? The objective for this video is to show you how to identify the support reactions if there's a three-dimensional object. And how do you draw a free body diagram of that? Then how do you use the equation of the equilibrium to solve the problem? Now the equation of the equilibrium will be expanded to 6 equations instead of just 3 equations. So when you have a three-dimensional problem, you're going to spend more time to solve the problem. So let's just look at some of the real application. Why do we care about the three-dimensional supporting system? This is a 6-way of the ball bearing, meaning this is like a house of a ball, and this can freely rotate in any of the direction. So this is what we call the ball and socket joint, and apply to many different places. It allows you have the maximum movement at any of the direction. Over here you see a bearing. So the bearing normally is a device that support the object, but it allows it to rotate. So when you can have things to freely rotate, that means there's no moment reactions. However, this housing here, this bearing house here and here, they are preventing this bearing or the shaft to move left and right and sometimes back and forth. So you will have a supporting force at this direction and this direction. So this will prevent it from moving up and down. This one will prevent it from moving left and right. But it can freely rotate. Okay, it can rotate without any other problem, and that is what we call a bearing. Another case is this one, not a mechanical device, but if you have some kind of a roof here that is attached with a cable to the wall, and this cable is on the angle of this roof to the point of A, which is right at the middle of this roof. So it's not like a perpendicular, it has an angle, and that is the case where you have a three-dimensional situation, right? So if you draw this one here, how do you draw the free body diagram? How do you analyze the force? How do you determine how big the cable that you should use? And that is the problem that we need to solve. Let's look at some of the example about the three-dimensional support. In the two-dimensional, we have only 3 cases. We have a roller, right? We have a pin, and we have a fixed. In the 3-dimension, you have several different cases, and let's look at this one here. This one just like you have a bar that has very smooth bottom, and you support things, and this allow you to have only the reaction force, which is perpendicular to the contact surfaces. And if the surface is the ground like this one, then the force is going to be perpendicular to the ground. This one is a journal bearing. So the journal bearing looks like this. You have a shaft going through this journal bearing. The journal bearing is a housing device, allow it freely rotate in this direction. Okay, and you cannot move left and right, up and down. So we have Fx, we have f of z, okay? But can it rotate in other direction? No, it can rotate in this direction. So in this direction, it can freely rotate. However, it cannot rotate in this direction. If it cannot rotate in that direction, you're going to have a moment in that direction. So you have a moment and a z, moment and an x. So how many unknown? You have 4 unknowns. Here is a ball and the socket, which is the case we just show you with a picture. Yellow color, a big ball. We said this will allow the device to rotate with a maximum angle. So you can freely rotate in any of the direction. However, you cannot leave the socket here. So there's supporting force F, X, Y, and Z. You have 3 unknowns. This is something that we all see in our house. There's a single hinge. The single hinge allow it to rotate, right? So when you want to open like a door or a closet, then you have probably this kind of a single hinge. It allow you to rotate, but it allow you to rotate in one direction. And this is the direction you can freely rotate, right? Then this hinge prevent this hinge to freely move because you have a nail at here, you have a nail at here. So since it cannot freely move, you are going to have a reaction force, which is the Fxy. And here, 3 different forces to prevent this hinge to move around, right? You not expect this will move around. You are not allowed this hinge to rotate in this direction. You don't allow the hinge to rotate in this direction, so you're going to have a reaction moment, but you do allow it to rotate in this direction. So how many unknown? You have 1, 2, 3, 4, 5. 5 unknown. So you have 4 unknown here, 5 unknown here, 3 unknown here, 1 unknown here. It is just depends on the situation, and there's a table in your textbook. I encourage you to look at the table to understand different device, what is the reaction force. Here we wanted to give you an important idea. When you have more than one bearing or one hinge like acting on a device, the previous one we see, if you have a hinge, you are allowing it to rotate a certain direction, but you don't allow it to rotate as the other different direction, then you're going to put the resistive moment. But if you put multiple hinge or multiple bearing, you don't need to put those moment reaction force anymore. That is because the design of multiple bearing would not allow it to rotate at any way. So you only just need to put the reaction force, and you don't say, oh, this is not going to rotate in this direction, so my M of Z will be one of the none. No, not this case. Similar to this one here, that you have a bearing at here, you have a hinge at here, because both of the things exist, then you don't need to worry about the preventive or the reactive moment anymore. Now, so what is the equation of equilibrium for three-dimensional cases? Three-dimensional. Now it's the same idea. You're going to have a net force equal to 0, net moment equal to 0. However, force and moment are vectors. How many force can you have in 3 dimensions? You can have 3 different components, x, y, and z. So that's why you have this equation right here. For moment, if that is the planar force case, you have only one direction, which is perpendicular to the plane. If you have three-dimensional, the moment could be any directions, meaning the moment could be x, y, and z as well. So summation moment equal to 0 also give you three situations, which are these three. So when you are dealing with three-dimensional, the maximum equation you could have is 6 equation, meaning you can solve 6 unknown. That is very complicated situation. Now let's look at the constraint and statistical determinacy. We talked about this before. When you have more of the equation than the number of the unknown, or you have the number of the equation which is less than the number of the unknown, what do? If you don't have enough equation than the unknown, you cannot solve the problem. So it's called the indeterminate problem. That means you have more unknown than the equation of the equilibrium, which in this case is a 6. But if you have more of the equation than the unknown, then you have the opposite situation, which means you can choose any of the equation to solve the problem. Let's say you have a three-dimensional problem, you have only 3 unknown, and you have 6 equations to choose. You can pick any of the 3 equations then to solve the problem and choose. And based on the experience, sometimes if you choose the equation correctly, you can solve problem more faster and quickly. So so then the problem is that if we only need to have enough equation to solve the unknown, why do we still have this kind of a situation that we have more unknown than the equation of the equilibrium? So this is a problem called the improper constraints. If we have a support to prevent things to either move or to rotate, in the three-dimensional situation, we have only 6 equations, and each one of the support will create a different number of unknown, depends on what kind of support that you have. In this example, you can see here that we have a support at A, we have a support at B. And both of the support are the ball and socket support. So when you have ball and socket support, it's freely rotate in any of the direction, but it prevents it from moving. So you have A, X, A, Y, A, Z, B, X, B, Y, B, Z. You have 6 unknowns, right? And it looks like you have 6 constraints and you have 6 unknown, you have 6 equations, you can solve the problem. However, this is not the case because this one still allow it to rotate. The summation, it will allow you to rotate in certain direction, but you don't allow it to rotate in the AB direction, right? That means you cannot make this one to rotate up and this one rotate down. So to prevent it from rotating, we need to give more support, so it will prevent it actually freely rotate in any of the direction. Let's look at an example and to do some real calculation for the three-dimensional case. In the first example, we're going to show you we have a rod. This is the L-shaped rod. And at the point of A, we have a bearing. At the point of the B, we have a cable that going to the roof. At the point of the D, we have a going down force 80 pounds acting at the point of D. And we want to find the reactions at the thrust bearing A and the cable of the BC. So how many unknown that we need to solve? Now, the first thing you do is to establish your coordinate. And we are already given with a coordinate x, y, and z at here. Then we need to draw the free body diagram. For the free body diagram, including how the reaction force are or moment. This is a bearing. What kind of a reaction force do we have? We have reaction force at the x direction. We have reaction force at the z direction. What about this cable here? Then we have a cable, which is going to give us a tension force. Once you identify those, then we can use the equilibrium equation to solve the problem. So this is a bearing, but we only have single bearing, right? When you have a single bearing, you not only have the reaction force, you also have a reactive moment as well. And which we talked about this in the previous few slides. Unless you have two bearings or more, then you don't need to worry about this reactive moment. But over here, we only have a single bearing, then you have to consider those as well. We have a tension force here. We have AX, AZ. We have two moments. How many unknowns do we have? We have a 5 unknowns. 5 unknowns. And we need 5 equations to solve it. And sometimes some of them are very easy to deal with. For example, if you look at the force that we have here, these two are in the z direction. This one is in z direction. This one in the x direction, and there's nothing else in the x direction, which immediately tell you this one equal to 0. So even though we have a 5 unknowns, now we shrink to 4 unknowns. And then you can sum the f of y, which is the force of the AD and BC and AZ. You sum them together is going to be equal to 0. So that's the second equation that you can come up with. The third equation, you cannot use the f of y because there's no y component force in any of the component here. So you have to use one of the moment equation to do that. When you do the moment equation, you need to select the reference point. And I always tell you, try to find the moment, the point that you can minimize things, right? So this moment here is the z direction moment. This moment here is the x direction moment. And what is the y direction moment? The y direction moment is going to be 0 because there's no reaction moment in the y direction. So when you sum the moment in the y direction, and y direction is going to rotate about like this, right? Which will be caused by this force or caused by this force. And if you select the reference point, which is at this point, then this force is not going to give you any of the y moment as well because it just goes through this y axis directly. It interact with that y axis. So none of these forces will create any of the rotation around the y axis. So you only consider about the AD and FBC. That's why we put AD here, we have FBC here, then we look at the distance. One is 1.5, the other one is 3. Then you can solve the problem. You can solve from, can we solve the problem? Let's look at that. We have A sub z, we have FBC, and that's only 2 unknown, and we have 2 equations. So when you use this equation first, you can find F of BC, which is equal to 40 pounds. And then you put 40 pounds back into this equation, then you will find out AZ is going to be equal to 40 pounds as well. So that's how we solve the problem. You just need to pick the equation correctly to help you to find the solution. All right, so now if you wanted to find the moment equation, we just tell you use the point A is the best place to solve the equation. Let's look at another example here. Here we have a plate, and this plate is sitting on the X and Y plane, right? X, Y, and here's the Z. Sitting on the XY plane, you have 3 cables at each one of the corner of this rectangular. Only at the Z, or you can say the origin, doesn't have any of the support. And you also apply 200 pounds at this side, looks like a midpoint between the A and C point. Now, with this one stable? Well, you have a plate and you only support at 3 corners. It looks like it's not very stable, right? But when you apply a 200 pounds, maybe you can make it a little bit stable. But let's look at how we solve the problem. The uniform plate has a weight of 500 pounds, supported by 3 cables, which is this one here. Now, pay attention, there's a 500 pounds of the weight. So when you know this one, you're going to put the weight of the plate into this plate ridge body. We normally put the weight at the center, the mass center of the object. In this case, it's going to be just right at the midpoint here. This is the midpoint of the plate, and we know there is a weight going down, which is 500 pounds. And each one of the cable is going to give you a cable force going up, going up, going up, and also you have a pride pound, which is 200 pounds at this point. So to draw a free body diagram, this one looks very straightforward, very simple, and there's no device prevented from rotating. So let's look at the exact situation. This is the exact situation that you have as what I just described. 3 cable, tension force, external force, the weight. You have 5 forces acting on a plate. Then you apply the equation of the motion. Now, there's no X, there's no Y force, so don't even use those 2 equations. The only option that you have is going to be the Z direction, Fz equal to 0, and the other equation has to come in from the moment equation. So when you do the moment equation, and then you have to pick the point as the reference point, right? You can say this is the point A, and this will be your point C, this is your point of B. If you pick point of B to find the net moment, you don't need to consider about this force because this force goes through this reference point. So you just need to consider about the rest of the 4 points to find the moment around this point. And it is not, this one is the static problem meaning there's no rotation, meaning the summation moment at that point, it will be equal to 0. So you can pick any one of them, but I probably will pick A and B because they are right on the axis, okay? And it's easier to find the distance. If you pick point of C, then you have to figure out, well, what is the distance from here to here, right? And what is the distance from here to here? It will be a little bit harder to solve the problem. Well, this one is okay, but this one is a little bit challenging, but it's still doable. So you come up with a 3 equation and then you solve for 3 unknown because you have 3 cable force you need to determine in this case, and it's not super complicated. You can still solve it, and you can solve a number to be these numbers. Okay, so this is the end of our video about the chapter 5. We talk about two-dimensional equilibrium, which is the summation fx equal to summation f of y equal to summation moment of a reference point equal to 0. And three-dimensional, you have a summation fx, summation f of y, summation f of z. So you kind of extend this into one more dimension. For moment, you have a summation moment x, summation moment of y, summation moment of z equal to 0. This is for the rigid body, and it is static. Static meaning it doesn't move. That's why summation force equal to 0. If it's not equal to 0, you have acceleration. It doesn't rotate. That's why the summation moment are all equal to 0, and that is the case. We also talk about the two force member, and that is the member that you only have two force acting at the device, and it must be along the line of these two force points. Okay, the device itself could be like this, but you only apply force at this point and this point. This is still like a two force member. There's a discussion about three force member. We are not concentrate about that. If we are going to use that, we will talk about that. But you can read the material from the textbook. Three force member is not like this situation. If there's a three force member, they must to they must intercept at one single point, and or they have to be like a parallel. All right, so that's the chapter 5.